Hello, it's Laure. In order to understand virtual particles, we need to understand why we invented them, how space is not empty, how physicists represent interactions between particles, and the genius behind Feynman's diagrams. Then we will understand how virtual particles fit into this formalism. According to quantum field theory, vacuum is not exactly empty, it contains quantum fluctuations with observable consequences. We represent some of the observable consequences as virtual particles, but let's make it clear they do not exist. Virtual particles describe, they do not explain. As a result, the vacuum between interacting particles is not simply empty space. It fluctuates and contains short-lived virtual particle-antiparticle pairs, for example, pairs of leptons or pairs of quarks and gluons. These short-lived pairs are called vacuum bubbles. These virtual pairs can also appear when a photon propagates, for example. And some of these pairs, like the virtual electron-positron pair, are charged and can act as an electric dipole. We call an electric dipole the separation of positive and negative electrical charges within a system. In the presence of an electromagnetic field around an electron, the virtual particle-antiparticle pairs reorganize themselves and they counteract slightly the electromagnetic field. The field is therefore weaker than would be expected if the vacuum were completely empty. We call this reorientation of the virtual particle-antiparticle pairs vacuum polarization. And quantum physics is interested in computing the probability of different outcomes. Since interactions between particles can produce different outputs, we use the concept of scattering matrix or S matrix to describe the result of interactions. And in this domain, Richard Feynman had a genius intuition. The construction of an S matrix can be represented by diagrams where nodes and lines represent specific aspects of the computation. In scientific terms, the series expansion of S matrix elements arises from a perturbative treatment of the interactions. The elements of the series expansions are linear combinations of multiple integrals, where each integral can be represented by a Feynman diagram. Feynman diagrams look like this and follow the famous Feynman rules that you can find online and everywhere. The ingoing and outgoing lines represent the prepared particles as well as the detected particles. The lines internal to the Feynman diagrams are called virtual particles. Feynman had the intuition that all particles take all possible paths with a certain probability, with the limit that loops are infinite and cannot be given a probabilistic interpretation. Virtual particles are widely used as a shorthand language for complex integrals over internal momenta. And a virtual particle has a real mass, a momentum, a real spin, and a real charge. So informally they are viewed as transmitting the fundamental forces in quantum field theory. The electromagnetic force is transmitted by virtual photon, the weak force is transmitted by virtual Z and W, and the strong force is transmitted by virtual gluon. If you learned something, please give this video a like, and if you would like to know more, I invite you to watch another video on my channel.